This video is part of an online course on algebra and is about the real numbers. I could have as well titled this video Elementary Real Analysis. Usually in courses on algebra, it is assumed that the audience has a basic understanding of real and complex numbers. This is for practical purposes because it would take a considerable amount of time to develop the real numbers and complex numbers in an adequate manner. So typically the algebra courses just say that we will assume that you know the basic properties of real numbers. This is somewhat unsatisfactory simply because we are going to be studying vector spaces over R and over C primarily. Even though I will set up things so that the field is completely arbitrary, the most important results will be over R or over C, the real and complex numbers respectively. For that reason, I want to get into just the basic properties of real and complex numbers, just enough so that it doesn't seem artificial. So what I am going to do is, I am going to focus on only one key property of the real numbers. In fact, it is the property of the real numbers that makes it different from rational numbers. That is called completeness. I am going to be intentionally sketchy because the content of this particular video will essentially take 3-4 hours if I do it in full detail. So what I am going to do is I am going to be intentionally sketchy. I am going to give you a flavor of what proofs that use completeness look like and what completeness really is. I want to get into the guts of completeness. Now, what's the starting point of all this? Well, starting point is what you do is, imagine you have a line extending infinitely on both directions, and you mark some point arbitrarily and call it 0, the origin. And then what you do is you mark unit length. Now, customarily the unit length is always taken towards the right when you look at it from the top. Well, that's completely arbitrary. You can take it to the left also. It really doesn't matter. In fact, left and right don't even make sense unless I specify which direction you're looking in. But that's getting a bit philosophical. What I mean to say is just mark off a point 1. The distance between 0 and 1, that is going to be our common scale by which we measure distances. So the length between 0 and 1 is what is going to be considered as unit length. Now, once you have marked this, you can mark all the rational numbers on this line by placing a dot at the point corresponding to each rational number. For instance, let's say that I draw this green line. I mark this point as 0, this point as 1, then clearly half should come here, right? This should be the location of half. Similarly, you can mark 2 by 3, 3 by 4, all the rationals you can mark because now you have a common measure of what unit length is. Okay. So once you have done this marking, you might be tempted to think that every point on the real line, I shouldn't really say real line, every point on this green line that I have just drawn, you might be thinking that every point has been associated with a rational number. Okay. Now, the resulting set of points once you mark on this green line is what is, it's actually dense. Now, I am not going to get into the meaning of what dense means. What this really means is that there is no, whatever 2 points you take, there will be a third point that is in between these 2 points. That's what dense here means. It could also mean dense in what is called a topological sense, but that would take me much too afar from the contents of this course. So I will stop myself here. But essentially the point I want to make is, you might think that because all these points are clustering everywhere on the line, you might think that there is nothing left. You have exhausted the line. This is not so, and this can be seen by completely elementary basic fact. In fact, we have seen a proof of this. There are holes on this line. For example, there is no rational number R whose square is 2. We saw a proof of this way back. Okay. Now, the question is, how do we know that even though there is no number whose square is 2, no rational number whose square is 2, how do we know that there should be a number at all whose square is 2? Why should we expect there to be a square root of 2 in the first place? In other words, why is the square root of 2 a genuine whole? Well, let's look at this picture. It's a classical geometric argument. What you do is, you draw the green square that I have drawn is the unit square that is its base is the segment 0, 1 that we first marked off. And as we know from the classic at least 3000-year-old theorem, Pythagoras theorem, might even be much older than 3000 years, we know that the diagonal of this square has to be square root of 1 plus 1, which is square root of 2. Okay. So, there we have constructed just by constructing this square of side length 1 unit, we have constructed this diagonal whose length is going to be square root of 2. Now, why is this a problem? Well, now that you have access to this diagonal, you can just take a compass and easily draw the circle of radius root 2 centered at the origin. This will intersect the line at a point here, right? It will intersect at a point, and that point on the real line is actually a hole, right? I have marked it in dark white to indicate that it's a hole. That is not there when you mark out all the rationals. It is a point on the line that does not correspond to any rational number. So, geometrically we can see that there are points on the line which do not correspond to any rational number. So, consequently, the question arises, how do we plug these holes? Well, we do what is called completion. Okay? The real numbers are a completion of the rational numbers. This means that R is a set that contains all the rational numbers and also contains all the holes. That is, all the things that are left over when you mark the rationals on the line, they will also be corresponding to points in the set R. Now, R is not the only possible completion of the rationals, in the sense that there are ways, there is something called a complete field. There are other ways, the completeness, there are various notions of completeness. So, in one of the notions, the complex numbers can also be treated as a completion of the rationals. Okay? But the real numbers are the smallest. Like complex numbers will correspond to R2. So, clearly they plug in all the holes, but they will plug in a lot more. Okay? So, the real numbers are natural because they are the smallest field that contains the rationals and all the holes in the rationals as well. Okay? So, in this sense, the real numbers are the most natural completion of the rationals. Now, having said all this, I am going to dampen your spirits by saying that we are not going to engage in the construction of real numbers from rationals. There are many ways to do this. The two most popular ones are ones due to Dedekind and Cantor. Dedekind use what are called Dedekind cuts, and Cantor use what are called Cauchy sequences, and both constructions are extremely elegant, but if you were to write out all the details, it will fill up quite a number of pages, and really this is these constructions are best left for you to learn on your own. So, if you search construction of real numbers using Dedekind cuts, some noble soul in some university would have put up a detailed set of notes highlighting how you can construct the real numbers using Dedekind cuts, and analogously for if you search Cauchy sequence construction of Cantor's Cauchy sequence construction of reals, somebody would have put up a detailed set of notes highlighting how to get the real numbers using Cauchy sequences. Now, I am not going to do these constructions. Instead, as I have mentioned before, I will focus on what this completeness means. I have been talking non-stop about completeness, but I have kept you in suspense. I have not really told you what completeness is. We will come to that in the next slide. Okay. What is completeness? This property that is going to occupy us. The setup is an ordered field, and you have a subset S of that F. Okay. Now, I have not mentioned it here, but for sanity I am going to assume it is non-empty. It is not really needed, but I get confused about logic about the empty set, so I am assuming you will also get confused. So, for sanity I am just going to put non-empty. Now, we say that S is bounded above if there is some element B in the field such that no matter what element x you choose in S, the element B dominates X. Okay. So, the set S is bounded above if you can find an element to the right of the set in the field in some sense. Okay. So, now I am going to describe what completeness is. Start with an ordered field and a set S that is bounded above. A least upper bound or supremum is an element that has two properties. First of all, it should be an upper bound. I mean, it's called a least upper bound. It's something like GCD. So, first of all, it should be an upper bound. Otherwise, calling it the least upper bound is crazy. The second says that if you choose any other bound for S, that bound necessarily has to be greater than or equal to U. Okay. So, the least upper bound U is that bound which is lesser than all other bounds of the set S. Okay. So, the term least upper bound is sort of self-explanatory. We say the ordered field F is complete if every subset that has an upper bound also has a least upper bound. Okay. So, if you are seeing this for the first time, I am fairly certain you are puzzled. We talked about holes and plugging in the holes, and now I give you a property about bounded sets in an ordered field. I say that the field is complete if every subset that has an upper bound also has a least upper bound. It seems to be that there is no relationship between what we want and what I have given you. Well, this is always the case in mathematics that is at least 150 years old. What has happened is, it's not as if this definition sprang out from space, right? People would have explored what exactly does it mean to fill in the holes. And after sufficient exploration, somebody would have come up with that property that most crisply captures what we want. But because that several years of thought has been skipped, necessarily a textbook cannot summarize everything that happened that led to this definition. Unless the textbook wants to be a library in itself, it's simply not possible to historically tell you exactly how what the genesis of this definition is. But what I could do is, I could sort of tell you what could have possibly gone on in a short way, not adequately, but enough so that the puzzlement can be reduced somewhat. So, let us think about what this is trying to say. Look at the set Q, the field Q. Well, this is not complete. We know that, right? It should not be complete in this sense, simply because otherwise this entire video is a complete waste of time. So, Q is not complete. Now, what is it lacking? Well, what you do is you set up the following set in Q. I am going to call that set S. This set is the set of all x in Q such that x squared is less than 2. Look at the set of all rational numbers whose square is less than 2. Now, this is clearly a bounded set. Set that is bounded above in Q. Why? Because 2 is an upper bound. 2 is clearly an upper bound for this set. What is the candidate least upper bound? Please pause the video and think about it for a couple of minutes. I am fairly sure many of you have realized the candidate least upper bound is not in Q. It's the number square root of 2, right? So, what is happening is, every hole that occurs on the line, you look at the set of all rational numbers that are to the left of that hole. That set is a set that is bounded above, and this hole is the least upper bound. Okay? So, essentially it is this completeness that is lacking in Q, and you can sort of see from this brief example why somebody wanted to capture these holes using this strange property of completeness. Okay, I am sure I have reduced the puzzlement by half at least. Let's go all the way and make the puzzlement 0 by trying to understand the consequences of this somewhat complicated looking definition. First, let's see some basic properties. The supremum of a set S, if it exists, we denote it by sup S. As I have mentioned many times before, mathematicians are very creative in a lot of ways, but not when it comes to giving names. We give the most bland and straightforward names. The supremum of a set need not be an element of the set. Okay. For instance, I am going to introduce what are called open intervals a couple of slides down the line, and you will see that there these open intervals, the supremum is not there. I mean, I can do it right away. You can just look at the set of all for instance x in Q such that a less than x less than b, where a and b are fixed rational numbers. You fix two rational numbers a and b and look at the set of all x in Q that are greater than a but less than b. Now, this clearly has a least upper bound, and the least upper bound you should check. It's a very easy exercise in the definition. You should check that the least upper bound is in fact the number b. The number b is clearly not there in this set. Okay. Anyway, I am going to define this as an open interval very soon. Now, coming back, if the supremum happens to be in the set S, then we say the supremum is the maximum. Okay. So, maximum will always be there in the set. Maximum need not always exist. Supremum also need not always exist. Even if the supremum exists, it need not be the maximum. Okay. So, I hope you can unwind everything I said very quickly. In a completely analogous way, we can define the greatest lower bound or infimum, denoted inf S, of a set S that is bounded below. It is an instructive exercise to do it once. You have seen one definition. I am just asking you to make less than greater than. Okay. So, please do that so that you have a better understanding, and I should say that I am intentionally not giving many examples here, because that is not, I mean, when I do not give sufficiently many examples is when I feel that you coming up with the examples is more worthwhile than me presenting them. Whenever the example is needed to illustrate what is happening, I will definitely give you examples. So, please sit down and write some sets in Q. You can also write down sets in R. You have an intuitive idea of what R is. You have been working with R at least for a few years from school. So, write down some sets, see if there is supremum. What is the supremum? When does set not have supremum in Q? When does a set not have supremum in R? Just explore this so that you have a better understanding of what is going on. Okay. Now, the supremum of a set, if it exists just like the GCD, is unique. That means a set S in an ordered field that is bounded above cannot have two supremums. Now, here is a characteristic type of proofs in mathematics that I really like. I mean, I think I have mentioned this before, but there is no harm in repetition because I might not have mentioned it. So, it might not be a repetition. Even if it is a repetition, it is very useful. So, in mathematics, to prove that two things are the same, or rather to prove that there is only one of a thing, what we say is assume that there are two things. Then we say that these two things are the same. So, to show that something is unique, you assume that there are two of them and say that both of them are the same. It is something that is really crazy and I really like in mathematics. So, we want to show that the supremum is unique if it exists. So, what you do is you say let U and V be both supremums, of S. That is, I have two supremums for the same set S. Now, let us look at the definition. That means both U and V, did I call it U and V? Yes, I called it U and V. Both U and V are upper bounds for the set S. Okay. And the second property says that if B is any upper bound for S, then that upper bound has to be definitely larger than or equal to U. So, what this immediately gives you is that u is less than or equal to v and v is less than or equal to u. I'm going to ask you why. Please pause the video and think about why. This is utterly trivial. It should not take you more than the time for me to finish this sentence to get this. I hope you got it. It's because since v is an upper bound and u is supposed to be the least upper bound, u has to be less than or equal to v. And similarly, because v is the, I shouldn't say least upper, the least upper bound, since v is a least upper bound, this doesn't even make grammatical sense, but I have to say it for the sake of argument. If v is a least upper bound, then u is an upper bound, therefore v must be less than or equal to u. So the net upshot is u is equal to v. Okay. So this shows that the supremum, if it exists, is unique. Now we come to a very useful characterization of the supremum, which we will repeatedly use in proofs. It gives us a handle whenever you have to prove something about completeness or supremum. This gives us a handle of how to hold it and tackle it. Okay. So take a non-empty set that is bounded above. This is going to characterize the supremum completely. An element u in F is the supremum of S if and only if, first of all, it is an upper bound of S, and if you take any number that is positive, typically it is called epsilon, that is for historical reasons we always call really small positive numbers epsilon. There exists an element S in S such that u minus epsilon less than S less than or equal to u. What this is saying is the least upper bound is that upper bound with the property that if you knock off a little bit from that, that is what u minus epsilon is doing, you are slightly chopping it, then there must be an element of the set that is greater than u minus epsilon, greater than or equal to u minus epsilon. That is, if you slightly chop it, you will enter the set S, or at least there will be an element in the set S that is large, dominates u. Okay. Why is this true? Now I am going to try to verbally do this proof without writing down, so that you pay attention with your ears, register it in your mind, and then transfer it via your fingers on piece of paper. So I want you to listen to the proof and write it down by yourself for your own education. Okay. How does the proof go? It's an if and only if condition, and you have to prove both directions. Here both directions are not too difficult. Usually what happens is one direction is non-trivial, other direction is completely trivial. Here both directions involve slight amount of work, nothing difficult. Okay. Now start by assuming u is the supremum. Well, we have to show that it is an upper bound. Well, that's obvious because a supremum is the least upper bound, therefore it's an upper bound. And it should also have the property that if you knock out a little bit from it, then there must be an element S that dominates it. Well, why is that the case? Suppose it is not true. Suppose this is not true. There is no element S which dominates u minus epsilon. Then it is clear that u minus epsilon is also an upper bound for the set S. Consequently, u minus epsilon is an upper bound which is smaller than u, which is not possible because u is the least upper bound. So that shows that the supremum is an upper bound with the property that when you chop off a little bit from the supremum, you will always be dominated by some element of the set. On the other hand, assume that u is an upper bound and it also has this property. We have to show that it's the least upper bound. So what you do is you start with any other upper bound v, you have to show that necessarily u is less than or equal to v. Okay. So unfortunately I may have to break what I said because I am not able to keep track of things. I am being forced to write down. So there is an element v in F such that, suppose there is a v in F such that v is an upper bound, but v is less than u. Okay, but v is less than u. Now, if you think about this for a second, what this property will tell you what this property will tell you is that there is an element, there exists S in S such that V is less than S. Okay. Please think how this property, which involves an epsilon, actually gives you a V, gives you an S in the set that beats V, that dominates V, that is greater than V. But this is simply nonsensical because V is supposed to be an upper bound. How can you have a set element S in the set S which dominates V? That's simply not possible. So this is a contradiction. This is a contradiction. Okay. So due to my inability to keep too many things in my head, I am forced to write down, but that doesn't excuse you. Whatever you have learned from what I have said and what I have written down, please, pardon the pun, complete the proof. Please write down a full proof of this characterizing property of the supremum. This is going to be repeatedly used. In fact, I wager that any proof that uses completeness in real analysis almost surely uses this property, this characterization rather than the definition. Maybe there are a handful which directly use completeness. Almost all of them use this. It's very useful. Okay, whenever you're dealing with supremums, that is to say. Okay. Now, this is a fact. It's completely trivial. It's so trivial that most textbooks do not mention this fact. I just want to highlight it. I'm not going to give you the proof. You can do it yourself. It's completely trivial, but I just want to note it down so that you don't get confused if you see this type of argument in an analysis book. Arbitrarily close elements in an ordered field. You cannot have elements that are arbitrarily close. What do I mean by that? If you are in an ordered field, if F is an ordered field and you have two elements such that no matter what positive epsilon you choose, we have mod x minus y is less than epsilon, then x must be y. That is, you can't have two elements that are so close than any pre-specified level of closeness. You can think of epsilon as specifying how close x and y are. This is saying that no matter how close you think x and y should be, x and y is in fact closer than that, right? They are arbitrarily close to each other, then x must be y. This looks completely obvious, right? But it requires one line of proof, and that one line is usually taken for granted because it's so obvious. I'm not sure whether I'm going to use it in the proofs that come, but it's good to keep a note of this. Okay. Now what I'm going to do is I'm going to spend the next 30 minutes or so in an attempt to convince you that completeness, the abstract definition of a complete ordered field that we have given, characterizes lack of holes. That is, I'm going to convince you that a complete ordered field cannot have holes. Okay. So let F be an ordered field and let A comma B in F with A less than or equal to B. We define the following sets called intervals. What are these sets? Well, the open interval AB, which is the set of all x in F such that A is less than x less than B, and closed interval. So this is called open interval. Open interval. Note, it is possible for open interval to be empty. If you choose B to be less than A, then there is no element which satisfies A less than x less than B. So open interval can be empty. Closed interval AB is x in F such that A is less than or equal to x less than or equal to B. Again, the empty set can be a closed interval. This is called a closed interval. Then we have some counterparts which are usually called left close right open and left open right close intervals that are defined exactly in the same way. Okay, you just have to put equal to less than or equal to in one side, less than in the other. Okay. Now here comes a very important fact in real analysis which is used extensively. For our purposes, it is going to illustrate why a complete ordered field does not have any holes. So, let F be a complete ordered field and let I, so there is a typo here, this is II. Let II be a collection of, so it is an index sequence, index collection of intervals where the index comes from the natural numbers. So, you have a collection of closed intervals indexed by the natural numbers, and the key property is that these intervals are nested. These are closed intervals, so they are intervals of this type. So, the key fact is they are nested. What I mean by that is ij plus 1 is a subset of ij. Please recall, this does not mean proper subset in our notation. This just means it is a subset. It could happen that ij plus 1 is the same as ij. Okay? Then intersection of I equal to 1 to n, ii is not an empty set. It cannot be the empty set. Okay? So, I must mention the collection of closed non-empty intervals. Okay? I should mention non-empty because somebody could potentially choose B to be strictly less than A, then there is no element x in F that satisfies this. So, technically by the way I have defined, the empty set is also a closed interval. Some people exclude explicitly that the empty set is a closed interval, but the way I have written it, the empty set can be a closed interval because I do not specify that A is required to be less than B. Okay. These are just matters of notation, so do not be too worried about that. We just have to be careful. I am putting non-empty just to be careful. Okay. Then the intersection is non-empty. If you have a sequence of non-empty intervals that get smaller and smaller, I mean not necessarily smaller, they could stay the same also, then the intersection cannot be empty, and this crucially requires completeness. Let us see a proof of this. So, the first step is to give names, right. So, let II be equal to AI BI, closed interval AI BI, where AI is less than or equal to BI. We are now guaranteed that AI is less than or equal to BI simply because we are assuming the intervals are non-empty. Now, having said that, the property that ij contains ij plus 1 immediately tells you the following. It tells you that AI is less than or equal to AI plus 1, which is less than or equal to BI plus 1, which is less than or equal to BI. This is the meaning of ij, so I should probably write j here. Yes, ij contains ij plus 1 means if you draw a picture, if this is aj, bj plus bj, then aj plus 1 is here, bj plus 1 has to be here. Okay. Necessarily aj plus 1 has to be to the right of aj and bj plus 1 has to be to the left of bj. Okay. So, by the way, when I say right and left, I always put my hand to the right and my hand to the left. Now, I am spatially a little bit clueless. So, when it is recorded on the camera and displayed on the screen, whether it will really correspond to right or left or its mirror image, I do not know. So, when I say right or left, I am always saying to my right, to my left. Okay. Now, what do I want to say? Yeah. So, aj is less than or equal to aj plus 1, which is less than or equal to bj plus 1, which is less than or equal to bj. This is true for all j in n, which means each bj is an upper bound for the set of all ai's as I runs through n. look at the collection of all the left endpoints of the various closed intervals that you get in this index family of closed intervals. Put all the left endpoints and put them in a set. Let's call the set a name. Let's call it as. Then every single bj is an upper bound. Every single bj is an upper bound for this set. Now that means by completeness, let U be supremum of S. Let U be supremum of S. Okay. Then by definition, AI is less than or equal to U, but every single bj is an upper bound and U is the supremum, it's the least upper bound. So every bj should beat. Every bj should beat U. So this is true for all I comma j coming from the natural numbers. Okay. So in fact, I could have just said I here. I needn't have used a different index. I could have just said I here. It makes no difference for each I in N. So AI is less than or equal to U, which is less than or equal to BI. This is just a way of saying U belongs to AI, BI for each I in N. That means we have found the candidate element U is there in the intersection over I of II. So this particular supremum, whose existence is guaranteed by completeness, is that element which will be there in the intersection of every single II. Okay. So what we are essentially doing is, we have this sequence of nested intervals and you are dominating the left endpoints by the right endpoints. Therefore, the set of left endpoints will have a least upper bound. That least upper bound will be by definition dominated by every single right endpoint. Therefore, it will be there in every single interval. Therefore, it will be there in the intersection. That's all. The proof is rather trivial. Okay. Now we come to the second property that is true in a complete ordered field. Together, the first property and second property, I will use the first property and second property to make a case that a complete ordered field does not have any holes. Okay. Now, the Greek mathematician Archimedes is said to have remarked, give me a lever long enough and a place to stand on and I shall move the earth. So this is a very famous principle. It's sort of, I think he said this after he proved what is now called the law of levers. Okay, it's one of the results in classical statics. It's called the law of levers. I think he said this after he proved the law of levers. Interestingly, his proof of the law of levers is completely mathematical. It's worth looking at it. Just Google search proof of the law of levers by Archimedes. It's very interesting and it ties up to what is happening in this course. In any case, this is what you translate what this statement is. It's called the Archimedean property, named in his honor. Let F be a complete ordered field. Let X and Y be both positive. That means they are both greater than 0. Then we can find a natural number n such that nx is greater than y. So this is why this is saying give me a lever long enough and I shall move the earth. So what this is sort of saying is that y is supposed to be the earth. It could be very large. X is supposed to be v. That is Archimedes. It's supposed to be Archimedes. Now X could be really small compared to Y. It could be the case is Y is 1 googol and X is 1 by 1 googol, right? In that case, X is very small compared to Y. What this is saying is, if you multiply 1 by 1 googol by a number that is so large, I don't know how much it is in this case, let's say 1 googol squared will probably work, or 1 googol cube will definitely work. If you multiply X with 1 googol cube, then you will be greater than 1 googol. That's what this is saying, right? So now the eagle-eyed sharp reader or audience, listener in this case, might object. How can you multiply a natural number with an element of a field? That doesn't make any sense, right? That doesn't really make any sense. Well, as we have mentioned, the natural numbers are contained in every single ordered field. In fact, the rationals are always contained in every single ordered field. Okay. So therefore, it does make sense to say nx, or you could also take it as a shortcut for x plus x plus x plus x plus x n times. Both are the same. In fact, if you remember, that's how we got the natural numbers as sitting inside any ordered field. We just looked at 1 plus 1 plus 1 plus 1 in the field and said that n times is nothing but the natural number n. Okay. So in any case, we will always assume that whenever we have an ordered field, Q is sitting in there happily. Okay. Now, how do you prove this Archimedean property? Well, you have to use completeness. So, we have to set up a set S whose upper bound will somehow give you what you want. So, what you do is you set S to be the set Nx as n ranges through n. Okay. Now, if it so happens that this set, if it so happens that Nx never exceeds y, if it so happens that y is always greater than or equal to nx, it never happens that nx is greater than y, then if nx is always less than or equal to y for all n, for each n in n, then y is an upper bound, for the set S. If nx can never dominate y, then y is an upper bound. So, let u be supremum of S. This is a set that is bounded above and we are in a complete ordered field, therefore, there must be a supremum. Okay. Now, here is a trick that I really like and I hope you like it too. If you have not seen it before, you will really like it. If you have seen it before, you are meeting a friend once again. Okay. An affectionate friend. Okay. What do? Look at u minus 1. You chop off 1 from the supremum. Okay. Look at u minus 1. Then by that characteristic property of supremum, there must exist n naught in n such that n naught x is greater than or equal to u minus 1. In fact, greater than, strictly greater than. If you chop off a little bit from the supremum, there must be an element in the set which is greater than this chopped off supremum, right? Now, you can see the most famous trick. This implies n naught plus 1x, one moment, look at, I have to change it slightly little bit, the proof has to be changed slightly, I'll have to do u minus x, not u minus 1. I have to look at u minus x, then say such that, yeah, I have to use x. X is a positive number, so I could as well use x in the place of 1. Chop off x from u. Don't chop off 1, chop off x from u. Then there must be an n naught such that n naught x is greater than u minus x, which implies n naught plus 1x greater than u. But that's simply nonsense because this contradicts u being the supremum of S. This contradicts u being the supremum of S. So that shows that this set could not have been bounded above. We have got a contradiction. So that means, this means S is not bounded above. So that means for some n, nx should beat y, it should dominate y eventually. Okay. So this concludes the proof of the Archimedean property. Now I am going to show a very useful feature of I mean, a very useful consequence of the Archimedean property. It's very useful because it doesn't use the full force of completeness. It just uses the Archimedean property and nothing more. Completeness implies Archimedean property, but Archimedean property does not imply completeness. We will see that in a bit. We won't give an explicit example, but we will see that. We'll mention that in a bit. What does this unboundedness of natural numbers says? It says n, the set n. One moment, something has happened. This set n is not bounded above in R. That is, there is no number, real number, that can dominate every single natural number. This seems completely obvious. But it still requires a proof, and the proof of that is just what we did for the Archimedean property. In fact, I am just not going to repeat the proof. I am just going to use the Archimedean property. What I am going to say is set x equal to 1 in the statement of Archimedean property, and you will see that the set n is not bounded above in R. So please complete the proof of this, and I also want to leave you with another exercise which is just a simple application of what we have just said. What that says is, given any fixed epsilon greater than 0, 1 by n is less than epsilon if n is greater than n naught. That is, more precisely, there exists n naught in n such that 1 by n is less than epsilon if n is greater than n naught. So the natural numbers are not bounded above. That means they become larger and larger. So what this says is that when you take the reciprocal of these numbers that get larger and larger, they get smaller and smaller. And how do you capture that they get smaller and smaller? You fix whatever positive number you want. It could be really small. Fix it. Then eventually, which is captured by n naught, eventually 1 by n will be less than epsilon. Okay. Now, these two are rather the starting points of the study of convergence of sequences. So if you are not able to get it, it's perfectly all right, but please do make an attempt. Please do make an attempt at solving how to complete this proof and why this follows from the unboundedness of the natural numbers. Okay. Now here comes a crucial theorem. It's called the nested shrinking intervals theorem. What this says is, if the intervals in the nested intervals theorem do really get smaller and smaller and smaller and smaller and smaller, then the intersection is not only non-empty, it has to be a single element. Okay. So let II, which is AI BI, again I should say non-empty for silly reasons, non-empty, be nested closed intervals in a complete ordered field. Assume further that for each n in n, we can find a natural number I such that Bi minus Ai modulus is less than 1 by n. What this says is, no matter what 1 by n you choose, the intervals eventually become of length less than 1 by n. So they are really shrinking, they don't stand still. They could stand still for some time, but eventually they will have to get smaller and smaller. Then this says the intersection of the intervals is a singleton set. There is only one element in the intersection. Okay. Now how do you show this? Well, we already know by the nested intervals theorem that the intersection of IIs is non-empty. This we already know, right? Now suppose A comma B is there in the intersection. Suppose you have A comma B that is there in the intersection. That means A comma B are there in each II, right, for every single I in the natural numbers. Okay, but eventually 1 by n will be less than mod B minus A, or I can just say B minus A because B is larger than A. I can assume, so I can assume B is greater than A. That's without loss of generality. Either A is less than B or B is less than A, because I am assuming that there are two different elements in the intersection. I am going to show that both are the same. So assume that there are two different elements. I can also assume B is greater than A. If A is greater than B, just reverse the roles of B and A. Just give them the opposite names. Okay. So in view of what I said, 1 by n is less than B minus A when n is large. What I mean by n is large is there is an n naught such that 1 by n is less than B minus A whenever n is greater than n naught. This follows from the second part that I left as an exercise for you. These 1 by n's become smaller and smaller. They can be made smaller than whatever quantity you pre-specify as epsilon. Here I am just specifying B minus A as my epsilon. So 1 by n will be less than B minus A, which means there is an interval, there exists an interval ij naught such that aj naught, bj naught minus aj naught is less than 1 by n. Okay, it's less than 1 by n. Okay, now I have written down a bunch of stuff. In fact, this completes the proof. Why so? Let's think about this. The interval ij naught is of length 1 by n, less than 1 by n. But A and B are supposed to be there in this interval, and the difference between them is greater than 1 by n. How is that possible? You cannot have two elements in an interval of length less than 1 by n whose distance between these two is greater than 1 by n. That's simply nonsense. So this contradiction shows A equal to B. Okay. Now I want to emphasize once more that the results of this particular slide use only the Archimedean property. This particular theorem, the nested shrinking intervals theorem, uses both the Archimedean property and the nested intervals property. Okay. Let's sit down and have a conversation. Our original objective was to get a one-to-one correspondence between the straight line and the set that contains the rational numbers but would have no holes, right? We want to find an ordered field or just a field that contains the rational numbers and has no holes and is in one-to-one correspondence with the straight line. Okay. Now I am going to sort of intuitively argue that the nested intervals property together with the Archimedean property captures the fact that there are no holes. Okay. Now to do this, I am going to sketch two proofs, two famous proofs in real analysis, and that should sort of convince you why this is the case. Now the second aim of doing this way is to demystify something. You might think that just the nested intervals property is enough to plug in the holes. After all, if you have a hole, you can just surround it by nested intervals and the intersection will have to be the hole. But the key fact is the nested shrinking intervals theorem requires the Archimedean property. So to get these smaller and smaller intervals that encircle a potential hole, we need to use the Archimedean property. Okay. Moreover, there are ordered fields that have the nested intervals property but not the Archimedean property. Okay. So technically what I have written here, The simplest example is the field of rational functions in one variable over the reals. The ordering there is somewhat weird. So, I am not going to elaborate how we can construct a field which has the nested intervals property but not the Archimedean property. So, this is an example of a non-Archimedean field. The ordering there is pretty weird, so I am not going to go into the details. But there are fields that have the nested intervals property but not the Archimedean property. Okay. So, let us get to understanding why having completeness removes the holes. Okay. And the way we are going to do that is really to show that you can trap the holes by nested shrinking intervals and then apply the nested shrinking intervals theorem to plug in the hole. The classic illustration of this is to show that in a complete ordered field there is always a square root of 2. We can find x in f such that x squared equal to 2. How are we going to prove this? I am going to just sketch the proof. If you are interested, you could fill up the details. You can skip it as well because this is not really the essential part of the course. I am doing this so that you have an underlying, you have an understanding of the underlying field R, which is going to come up repeatedly when we study vector spaces. Okay. We are going to first use the Archimedean property to construct a sequence of nested intervals that are shrinking and are going to surround the potential square root of 2. So, what is the candidate for square root of 2? Well, what you first do is you start by saying let M1 be the largest number, natural number. Remember, natural numbers are always there in the field. Let M1 be the largest natural number such that M1 squared is less than 2. Okay. Choose the largest natural number such that M1 squared is less than 2. We know what this natural number is, it is 1, right? We know what it is, but bear with me for notational reasons, I am calling it M1. Okay. Now, let us see what we have done. We have the line 2 is somewhere here, 0 is here, let us say 1 is here. Okay. Now, this is our M1. This is our M1. Now, the potential square root of 2 is either in this interval, it's either here or it's here. There are only two possibilities, right? It's either here because anyway 2 cannot be the square root of 2 because 2 squared is 4. So, we already know where it is going to be. It's going to be here, but again bear with me for a moment. It's either in the left half of the interval 1, 2 or the right half of the interval 1, 2. Okay. Now, what I am going to do is let M2 be either 0 or 1. Let M2 be either 0 or 1 depending on whether M1 plus M2 by 2 the whole squared is less than 2 or not. Okay. So, what I mean by that is if M1 plus half by 2 squared is greater than or equal to 2, if it's greater than or equal to 2, then choose M2 to be equal to 0. Okay. Otherwise choose M2 to be 1. Okay. Now, again we know that M2 is going to be 0 because we know that the square root of 2 is 1.4 something. right? So we know that M2 is also M2 is going to be 0, but I'm just writing the proof this way because what we are really doing is we are extracting the binary expansion of the square root of 2 digit by digit. I'm trying to figure out where the potential square root is going to be. Okay. Now, similarly, continue this way. Choose M3 in again 0, 1, M3 is 0 or 1, depending on whether M1 plus M2 by 2 plus M3 by 4 the whole squared is less than 2 or not. Okay. That is, if it so happens that M1 plus M2 by 2 plus 1 by 4 the whole squared is greater than or equal to 2, then choose M3 to be 0. If it's less than 2, choose M3 to be 1. And in this case, we actually know that M3 is going to be 1. So M1 will be 1, M2 will be 0, M3 will be 1, because we know that 1.25 the whole squared is less than 2. We know that. So similarly, you keep extracting the digits one by one. Okay. Now, what I am going to do is I am going to set up a sequence of nested intervals. I am going to set up a sequence of nested intervals. What is that sequence? Well, II is just M1 plus M2 by 2 plus M3 by 4. I mean, I continue like this. I am going to create further MIs in exactly the same way, plus dot 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 MI by 2 power I minus 1. I hope I got the index right. Comma, this is closed interval actually, comma, the same thing all the way except I put Mi plus 1 by 2 power I minus 1. Okay. This is going to be our II. Now, that is all the details I am going to provide for you. The sketch of the proof is actually over. What we have really done is we have trapped the potential square root of 2 inside these intervals II. By going digit by digit, what the binary expansion of the potential square root of 2 is, I have managed to trap square root of 2 in these intervals II. So, what you now do is show by the nested shrinking intervals theorem that intersection of the IIs is exactly one element. And you argue that this exact one element is none other than square root of 2. So this is the sketch part. I have spent some amount of effort in trying to tell you how to produce these intervals that sort of wrap around square root of 2. The intersection has to be the square root of 2. You finish the rest of the argument. Okay. Or you can just try to think about it. You need not write it down. As I said, this is really a part of real analysis, but to give you a flavor of what the real numbers are, I am doing this. Okay. Now this is actually a proof that is somewhat different from what is usually presented in real analysis textbooks. Real analysis textbooks, particularly the most popular one, the one by Walter Rudin called The Principles of Mathematical Analysis, maybe that book is the one that is most well known after Euclid's Elements, probably, I don't know. That book has what I call a rabbit proof of this. What a rabbit proof is, where you pull out some arbitrary numbers out of a hat, like a magician pulls a rabbit out of a hat. So you should, if you have time, look at the proof of the same fact that square root of 2 is there in the real numbers from chapter 1 of Walter Rudin's book. He will pull out a rabbit. So it will be a rabbit proof. I rather like this proof, even though writing down the gory details is a bit tedious, because it sort of illustrates how you actually get the square root of 2. There is nothing deep happening here. All I am doing is I am going to find out successively in which half of the interval square root of 2 is here. Okay. So we know that it's going to be here, then we know that it's going to be here, then I think again we know that it's going to be in this half, then finally it will shift to the right. So it will keep going, it will be either in the right half or the left half. So you just keep successively bisecting the intervals, and the intersection of those will have to be square root of 2. Okay, that's enough said. There is a square root of 2. Now we are going to do almost exactly the same idea to show that nested intervals property plus Archimedean property gives completeness. Why I am doing this is to show that what completeness really captures is the fact that you can plug any potential hole by surrounding them with nested shrinking intervals. I want to illustrate it once more in an abstract setting. The existence of square root of 2 was one illustration. This is another illustration. Again, I am going to be a bit sketchy because this is not really a part of this algebra course. I am doing it so that you have a good grasp of the underlying field R. Okay, and you should work out the details. If you are not able to, it's fine. Okay. Now I have to show that this ordered field that has the nested intervals property and the Archimedean property is complete. What do I do? Let's think. Notice one thing. If an ordered field has nested intervals property and the Archimedean property, then it automatically has the nested shrinking intervals theorem. The nested shrinking intervals theorem just use the nested intervals property plus the Archimedean property, right? You don't need completeness. If you have nested intervals property and Archimedean property, you have the nested shrinking intervals property. Please keep that in mind. Okay, now how am I going to sketch this proof? Well, let's take, for purposes I am just going to draw a line. We don't really know that complete ordered field means it's a line, but that is what we are trying to get at. So let's take the set S, which could be something, maybe a different color. It could be something. For simplicity's sake, I am going to draw it like an interval. Okay, really it doesn't make a difference. Maybe I can put a few more blobs and a few more points. It really doesn't matter. Okay. All that matters is this set S should be bounded above. This set S should be bounded above, and our job now is to, by hook or by crook, produce the supremum of this set S. Well, all we know is that the set S is bounded above, and that immediately by very definition gives you an upper bound. Let's say that upper bound is M1. Let's say that upper bound is M1. Now what I do is, I am going to assume that the set S is non-empty, otherwise again things are nonsensical. Every non-empty set that is bounded above must have a least upper bound. That is what completeness says. So what I do is I mark out a point, let's say S. Maybe I should call it cursive S, because otherwise you will not be able to distinguish it from the capital S, which is supposed to be, this looks like an 8. Maybe I will call it T. Take an element T that is coming from the set S and take an upper bound that is M1. Okay. Now, the least upper bound, if it exists, has to be in the closed interval that is in between T and M1. T and M1 are the left and right endpoints of the closed interval, and the least upper bound, we actually know that this green is the least upper bound. I have been sneaky and added a point so that my life is easy, but it does not matter. Even if this point x, what I have called green x, is not there, the argument is not any more difficult. But all I want to emphasize is that the potential least upper bound is there in this interval. Okay. Now we pull the same trick again and again. What we do is we bisect this interval, split it into two. Unfortunately, symmetry in life has played spoil sport. It looks like that green x is right in the middle, so I will draw it slightly towards. This is not really the center. I am splitting it in uneven way because somehow the green x has landed up exactly in the center. So pretend that this mark, this line that I have drawn is the center of the two intervals. Now, there are two possibilities. Either this is also an upper bound. Oh, I should write it in less ethereal ink. Also an upper bound. Either this is also an upper bound or it is not. Or it is not. Only two cases arises. Either this is also an upper bound or it isn't. Now, if it is an upper bound, call it M2. If it so happens that when you bisect, you call it M2. Okay. So that means now we know that the potential least upper bound has to be in this interval M2. So you can see what we have done. We have zeroed in on ground zero, right? By at least we are not zeroed in, we have lessened our error by half, right? By doing this. Okay, we have gotten closer to the green X. Now, what is the other property? The other property is if it so happens that M2 is not an upper bound. Is not an upper bound. Okay. If M2 is not an upper bound, you consider this interval M2, M1. So what you do is at each stage you are going to successively bisect the intervals and choose the one which is going to narrow in on the least upper bound. If you had chosen this, if M2 is not an upper bound, no matter how much you zero in, you are going to zero in on some random point. The least upper bound is not here, it is going to be here. Okay. So do M2, M1. Okay. Now let me for concreteness draw the picture again. Oh, I shouldn't draw it green. Let's say I am going to just reproduce a part of the picture. I am going to assume that we have chosen, so this is M2, this is M1. For concreteness sake, I am going to assume that the required least upper bound is there in M2, M1. It could have been there in TM2 also, but for concreteness, for illustrating, I am just going to say it is in M2, M1. Okay. Now, how does the proof proceed? Well, you should have guessed, you bisect this also. You bisect this. Call it M3. Well, I should be careful in giving the names because if I were writing down a proof, the way I am writing it down, the notation is going to be a bit hairy. So you carefully choose the notation so that bookkeeping becomes easy. I think it might be a better idea to call it AIs or something. You can carefully choose the name so that it's not that messy. Okay. Now bisect this interval. Okay. Bisect this interval into 2 and again figure out whether M3 is an upper bound or not. Is this an upper bound? Is it an upper bound? Upper bound. If it is an upper bound, then consider this interval M2, M3. If it's not an upper bound, consider M3, M1. Okay, and keep going like this. So in this way, we get nested shrinking intervals. Nested shrinking intervals. And as you can suspect, the intersection is a single point. Why is it a single point? Because as I said, the nested shrinking intervals theorem follows from the nested intervals theorem plus Archimedean property. You don't need completeness. Nested intervals property plus Archimedean property will give you the nested shrinking intervals theorem. Okay, easy to argue. Easy to argue that this point is the supremum. Okay. So what's the net upshot of all this? Nested intervals property plus Archimedean property is equivalent to completeness. And it also intuitively demonstrates why there are no holes in a complete ordered field. You can sort of trap the holes in nested shrinking intervals and the intersection will give you that hole was not a hole at all. Okay. Now, finally, after all this while, maybe almost 90 minutes, the last few theorems we have proved suggest that a complete ordered field has no gaps or holes. Well, I have repeated this intuition 3 times at least. Let me do it a 4th time. We use the Archimedean property to surround the hypothetical hole by shrinking nested intervals and use the nested intervals property to conclude that there is a point in the intersection which fills the holes. Now, we are not yet done. There is the issue of existence and uniqueness. How do we know that there is a complete ordered field? And how do we know that this is unique? Now, notice, as I said, you can have other completions of the real numbers. The complex numbers, for instance, also fills in all the holes. But the complex numbers are not an ordered field, that we will see in the next video. You cannot put an ordering on the complex field. Okay. So, there are other completions of R, like this complex numbers, but that lacks the feature of being an ordered field. And also you might wonder what I mean by C is a complete field, simply because if there is no ordering, you cannot talk about completeness. So, this issue arises because C is complete in a different sense. It does not have holes, but that is getting into topology. I do not want to confuse you. There are two notions of completeness which are not exactly the same. One is topological, one is this completeness. There is also another notion of completeness which has to do with algebra, but that is going to be even more confusing. Let us stop here. What I really want to say is, there is one and only one complete ordered field up to isomorphism. Okay? This is a very big theorem. In fact, showing the uniqueness is not that hard. Maybe I can put it as an exercise with some details. Showing that there is only one complete ordered field up to isomorphism is not that hard. Whereas showing that there is an ordered field that is complete is somewhat hard. You have to use either Dedekind cuts or Cantor's construction. And we will henceforth call this field the field of real numbers and denote it by R. Okay. So, I have wasted a tremendous amount of energy always saying complete ordered field, complete ordered field, complete ordered field. At all those places I can be more concise and just say R. I could just say R and I could have been done with it. Okay. Finally, I am going to bore you more with some more philosophical musings. We started off by saying that we want to fill in the holes left by the rational numbers when you lay them out on a real line, on a line. Okay. Now, as we have seen through several results, there are no holes on the real numbers, but how do we know that they model the straight line? For instance, as I said, the complex numbers are also complete in a different sense. They do not have any holes. Maybe what we have constructed as the real numbers is two-dimensional. Maybe it is not a line, it is a plane, or maybe it is some other geometric structure that we can't even imagine. It is well beyond our puny brains. We do not know, right? Now, to actually resolve this issue, we need to first understand what a straight line is. To say that the real lines model a straight line, you need to know what a straight line is. If you do not know what a straight line is, to say that the real line models the straight line makes no sense, right? You can only say something is true of something if you know what those two somethings are. So, what I want to say is a sort of an advanced remark. Under a suitable axiomatization of Euclidean geometry, not the classical Euclidean one which is sort of very vague, you can suitably axiomatize what a line is in Euclidean geometry. In that suitable axiomatization, it will turn out that the real numbers correspond one-to-one to the line. Every point on the line will correspond to a unique real number and vice versa. Now, this is actually a very subtle point, because many modern axiomatizations of Euclidean geometry have this ruler postulate, which essentially says that every point on the line corresponds to a real number and vice versa. So, there are axiomatizations of Euclidean geometry which really say that the real numbers and the line are the same thing. Now, that is not really going to solve the issue, right? Now, again, this is somewhat of a deeper point, and tackling this issue will take me far away from this course. It is done very nicely in this very interesting book by Hartshorne. It is called Geometry, Euclid and Beyond. So if you're interested, you should read the early chapters of Geometry, Euclid and beyond, where this is dealt with in a satisfactory manner, why the real numbers actually model a straight line. So that's enough philosophical musings, and it's been a really long video, so I'm going to bid adieu. This is a course on algebra, and you have just watched the video on the real numbers.